Hello, we are presenting a project in accelerating pointwise convolution inference in 3D reconstruction of point clouds. We, the members of this group, are namely Christine, Teodros, Daniel, and Emmanuel. In this presentation, we will walk you through the problem and motivation of this study, what we did regarding the subject matter, the method employed in this study, the baseline, our experimental approach, our results, and finally our conclusions. With regards to this research, implicit neural networks are key to our study because they can smoothly model 3D surfaces, fill in gaps from sparse data using length patterns, and optimize rendering end-to-end. These strengths make them perfect for high-quality 3D reconstruction. Methods such as a triplane approach reconstructs 3D shapes in an average time of 0.5 seconds. In light of this, reconstruction accuracy and inference remain the prime objective, and to this effect, impacts greatly its relevance in various domains such as VR and health. This translates to quicker delivery times for various applications such as generating quality 3D prosthetics. Contrary to traditional voxel and grid-based approaches, the baseline study uses a point cloud approach for a pointwise convolution in reconstructing shapes and objects. This entails sampling a pre-processed collection of a point cloud which passes through an FKA convolutional backbone for latent feature extraction. After retrieving the latent features, a neighborhood for a query is derived for further relative latent decoding, after which the occupancy of the query point is predicted. This process was applied to the ShapeNet dataset consisting of 13 shape classes. Despite the achievements of POCO, representations of objects such as point clouds are not evenly distributed, some having varied and more dense information for reconstruction. POCO assumes a uniform distribution across point clouds. To address this, we explore the use of a graph attention network to extract latent features that adaptively assigns weights to points with respect to its neighbors in a point cloud. This process helps to construct a more expressive model. This helps the model to update the features of each point based on relevant neighbors and thus pays less attention to irrelevant points, with the end goal of inference time reduction. In our approach, a point cloud is retrieved and passed through the graph attention network, and the latent representation is extracted through an MLP, and then a self-attention mechanism is applied to identify relevant points with respect to their neighborhood. Finally, a linear layer is reconstructed to predict the occupancy of a point to a surface. This study is benchmarked on inference time metrics, split over sampling inference, and mesh generation to assess speed. While an average time of 2.5 seconds was reported for mesh reconstruction, we observed a slightly higher time of 2.7 seconds on average over 100 samples. After our implementation, while obtaining a sampling time of approximately 2.7 seconds, the time to make inference was recorded as 0.0625. A mesh generation time of 2.6673 seconds was recorded. These results are based on average over 100 samples. In conclusion, the results suggest that a graph attention network backbone instead of an FKA conv improves average inference and reconstruction times, which also extrapolates to adaptability and generalization. Thank you.